This program is designed to introduce you to the 767 pneumatic system by describing the system operation and function of each of the major components in the system. The purpose of the pneumatic system is to supply compressed air for the following user systems: environmental control systems, thermal anti-ice, engine cross-starting, the air-driven hydraulic pump, the pressurization of the potable water, and hydraulic reservoirs. The primary source of compressed air for the pneumatic system comes from the left and right engines. Both operate in the same manner. Air is provided by each engine from either of two bleed sources: an intermediate pressure stage or a high pressure stage. They are both independently controlled. During climb, cruise, and certain holding conditions, as well as with high gross weights, the intermediate stage is supplying the air. Intermediate stage bleed air passes through a check valve before entering the system. During low power settings, descent, and certain holding conditions, the high pressure stage supplies the air. High pressure bleed air enters the system through a high pressure shutoff valve. The operation of this valve is controlled by the high pressure controller. The controller signals the valve to open or close as dictated by engine high stage pressure. This provides automatic switchover between the intermediate and high pressure bleed sources. The valve is either full open or closed. It does not modulate. When the system is operating using high stage air, the intermediate pressure check valve prevents reverse flow. For most operations, the intermediate stage will be supplying the air. Engine bleed air passes through the pre-cooler. The pre-cooler is a cross-flow heat exchanger which uses engine fan air to cool the bleed air. The two air flows are kept separated and are at right angles to each other inside the pre-cooler. The amount of cooling air passing through the pre-cooler is regulated by the fan air modulating valve. The operation of this valve is controlled by the fan air temperature sensor located downstream of the pre-cooler. It senses the temperature of the bleed air and pneumatically modulates the fan air valve to maintain the bleed air at approximately 380 degrees Fahrenheit. The pressure regulating and shutoff valve serves as the interface between the engine bleed air system and the airplane user systems. This valve provides three functions in the pneumatic system. First, it regulates the output pressure from the engine bleed system to a nominal 40 psi. Second, it provides airflow throttling for overtemperature control. This is accomplished by venting servo pressure and allowing the valve to move toward close. Overtemperature limiting begins at 450 degrees Fahrenheit by modulating the valve toward close. When the temperature reaches 495 degrees Fahrenheit, the valve will be fully closed. Third, it prevents reverse airflow into the bleed air system. Each of these functions can modulate the valve towards the closed position. Thus, the function with the greatest close requirement will control the valve position. There are two alternate sources of pneumatic air: the APU and ground pneumatic carts. The APU provides a source of compressed air for ground operation. Air enters the distribution system through the APU shutoff valve and check valve. The ground pneumatic carts provide the other source of compressed air on the ground. Air enters the system from either or both of the ground connectors. There are three isolation valves within the pneumatic system. Each isolation valve is driven by an electric motor to full open or full closed. Two of these valves isolate the left and right engine air distribution systems from each other. Both isolation valves have a bypass check valve installed. A center isolation valve is virtually identical to the other two isolation valves. However, there is no check valve with it. For normal flight operations, the left and right valves are closed, and the center valve is open. This center valve has a guarded switch to prevent inadvertent closure and loss of air to the air-driven hydraulic pump. The bypass check valves in the left and right sides of the system allow for flow around the closed isolation valves. This allows pressure from the left and right engines to drive the air-driven hydraulic pump. The operation of the pneumatic system is controlled from the flight engineer's control panel. 6 alternate action switches control the operation of the pneumatic valves. Gauges and indicator lights provide an indication of system operation. The pneumatic system has its own separate byte module. It is a microprocessor-based collector and storage device for faults in the line replaceable units or wiring interfaces associated with the bleed air system. It is capable of storing faults for the previous 8 flights, and in addition, it will verify proper system operation. This concludes the system overview of the 767 pneumatic system. This module will describe the operational check of the pneumatic system for the Boeing 767, equipped with either the Pratt & Whitney or General Electric engines. This operational check is designed to provide a high degree of confidence in component function after maintenance or prior to dispatch. The complete operational check with applicable warnings and cautions is described in Chapter 36, Section 11 of the Boeing Maintenance Manual. Consult this chapter before commencing an operational check. Caution: always apply electrical power before applying pneumatic power, and remove pneumatic power before removing electrical power to prevent possible damage to the equipment. With power provided to the airplane and the appropriate circuit breakers closed, the operational check can be performed. First, perform an air supply byte check. The air supply byte module is located in the main equipment center on shelf E3-1. Perform the byte check as outlined in the ramp maintenance manual or the expanded maintenance manual. If no faults exist, the pneumatic system is ready to be checked. In the flight compartment, on the P5 overhead panel, open both bleed air switches. The flow bars should show, and the off lights will be illuminated. Close the left isolation valve. The valve light should be illuminated during transit and then go out. Close the center isolation valve. The valve light should come on and then go out. Close the right isolation valve. The valve light should come on and then go out. Next, start the number 1 engine. Reference Chapter 80 of the Boeing Maintenance Manual for procedures, warnings, and cautions pertaining to engine starting. As the engine is started, note that the left engine bleed off light remains illuminated during the start and then goes out at the completion of the start cycle. With the engine started and stabilized at idle, check the pneumatic control panel on the P5 overhead panel. The left duct pressure should stabilize at 30 to 35 pounds per square inch gauge, or PSIG. The right duct pressure should read 0 to 5 PSIG. This simple check confirms bleed valve operation and high stage valve opening. Now start the number 2 engine. With the engine started and stabilized at idle, check the pneumatic control panel. The right duct pressure should read between 30 and 35 PSIG and is stabilized. Next, place the left and right pack selectors to auto. Increase the power on the number 1 engine. Check the pneumatic control panel. The right duct pressure should stay stable. The left duct pressure should increase to 45 to 50 psig, and then the pressure should drop. This pressure drop is proof that the bleed source has switched from high stage to intermediate stage. Duct pressure should return to 45 to 50 psig at above 50% N1 and stay there as the throttle is advanced to max continuous power. Now, retard the number 1 engine slowly. Duct pressure should drop to 20 to 25 psig, then jump to 45 to 50 psig, then decrease to 30 to 35 psig at idle. Perform the same test on the number 2 engine. The duct pressure readings on the right needle of the duct pressure gauge should be the same as for the left. With the tests completed, shut down the left and right engines using the procedures outlined in Chapter 80 of the Boeing Maintenance Manual. Next, return to the main equipment center and perform a bite check of the air supply bite module. If no faults have been recorded, the operational check is complete. Return the airplane to normal. This module has presented the Maintenance Manual operational check for the 767 pneumatic system. This check will assist maintenance personnel in identifying faulty components within the system and provides a high degree of confidence of correct system operation.
This video presentation will address 2 operational procedures which, when implemented, can improve the dispatch reliability of the 767 bleed air system. We will discuss the HPSOV and explain how its sticking at or near its closed position can cause erroneous cockpit indication. We will discuss the interaction and cockpit indication of the HPSOV and PRSOV. All procedures presume a flowing bleed air system with air conditioning packs on. The high-pressure shutoff valve, or HPSOV, has had a history of sticking either in the fully closed position or slightly open position. This can cause cockpit lights to fault either the HPSOV directly or falsely fault the pressure-regulating shutoff valve, or PRSOV. There are 2 operational procedures to help eliminate this problem. First, if the HPSOV sticks slightly open, the bleed light appears during the engine start. To prevent this from occurring, it's recommended that the bleed system be turned off prior to the previous engine shutdown. This has the benefit of using engine air to help the HPSOV to close, and prevents the HPSOV from being faulted during the next engine start. The second procedure is that if the HPSOV is stuck in the fully closed position and thus does not allow air pressure to the PRSOV, then the PRSOV is falsely faulted. With the engine running and the bleed air switch on, illumination of the bleed air switch off lights indicates a failed PRSOV. However, if the HPSOV is stuck closed and is not allowing air pressure to the PRSOV, it cannot open, as it must have at least 10 pounds per square inch air pressure to do so. The procedure is to advance the engine throttles to an N1 reading of 41%, which will result in additional air pressure to the PRSOV and assist its opening. If the light extinguishes under these conditions, the PRSOV is proven functional. When the engine is reduced to idle and the bleed air off light illuminates, this indicates that the HPSOV did not open and must be replaced. However, when the engine power is reduced to idle and the bleed air off light remains extinguished, this indicates the HPSOV opened and is satisfactory. So in review, it's suggested that two procedures be implemented. First is to turn off the bleed air system prior to shutting down the engine, which addresses the stuck, slightly open case. This will prevent a bleed light from illuminating following the next engine start. The second procedure is to advance the throttles to see if that will cause the stuck valve to open and extinguish the bleed-off light.